Hello, hello. We are we are starting. We are starting our first meetup. So first of all, we want to thanks to all of you who joined from different places. To introduce myself, my name is Sergey. I am one of the organizers of Data Science Society, and probably, yeah, I will just show you a little bit more about Data Science Society and the event which we organize together with the SoftServe. So we are partnering with different uh, organizations. If you know, I mean, our website, Data Science Society, what you can see that we are a volunteer organization, which we the main driver for us is to have the community around it, to share knowledge, to have fun, to have different, not only such kind of events like a meetup, but also we did a lot of virtual datathons, monthly challenges. We also did a lot of events where in workshops where people try different stuff. As a volunteer organization, we have one core team, we have a lot of mentors, we have also and volunteers who helps on different areas. So here probably something which is new, and because we were a little bit shy the last year with this COVID stuff, is that we decided to have three main direction. The first one is to start the meetups. First, our intent is to make them physical, but because of the COVID, we start the series with the online one. So our main person who is driving and responsible for the meetups is Yana. The next events are we are going to make like Saturdays where people from different expertise will be gathered and solve different problems. But this will come once this with the lockdown finishes, once people are start feeling comfortable and, yeah, just get together. About our other main core drivers, Stefan, who is responsible for the content, Todo, who is helping us for video stuff, and all the rest. I mean, there are so many people. So here, why we are here, it's because of the the event which we are starting together with the SoftServe. It was interesting that after probably 2 years, because we have initial discussions with them. At that time, they were still building a team, or there wasn't something that they can show or share, and that's why I'm so happy that finally we have two good speakers with very interesting topics. Something about the meetup and the meetup forms. We are going to make them each month. Up to now, we have more than 25 topics and speakers suggested. The form is going to be with the leading speaker and co-speaker. The leading speaker is going to be like how Roman it is a principal data scientist who will cover different topics from a high level, and then we will have the other person who can dive deeper into particular cases, particular uh, problems like Hristo is going to do. So if any of you is willing to share something or have an interesting case or have a diploma or something like a case where he wants to share it, to contact us via Facebook or LinkedIn channel. Yeah, now we have problems with our email, so don't use the email, please. And now uh, about the event, we will have two speakers. At the end, there will be a Q&A session. Uh, for simplicity, use the chat. So chat panel, I will just open now and say write your comments or questions here. So please use it. We will monitor only this channel for questions, and we will not unmute someone to speak about its question. Uh, so first of all, about SoftServe. SoftServe is a Ukraine company. They have a big office here in Bulgaria, and they have a lot of customers from various places. I don't want to dive deeper about what they are doing and what their data science team is doing. I think that Roman and Hristo will reveal the secret. And about the Roman is again from Ukraine. He's our first speaker. He's a principal data scientist. Something interesting. He has been in Bulgaria several times, particularly in Bansko. So I assume, Roman, you can share about our shopska salad, and did you find what the rakia means? And yeah, let's start. And Roman will show some good practices which they are doing in SoftServe with some real cases where their data science groups were challenged, and they find a solution. So Roman, go ahead.
Yeah, hi guys. Thank you, Sergey, for the intro. Yeah, being in Bansko was a pleasure. To be honest, I don't remember the exact dishes, but it was delicious for sure. Let me share my screen. Okay, you should be able to see my screen and deck. I think you do. Cool. So once again, my name is Roman, and I'm a principal data scientist at SoftServe. I'm leading a team who's responsible for the energy manufacturing inside data science group at SoftServe. We are that big that we have a separation between what we are responsible for. My personal background is computer vision and digital signal processing. But that was years ago, and now I'm mostly um, advising and promoting any data science inside SoftServe and outside. Say, data science practice at SoftServe. We started like 8 years ago, and we are now about 70 people grow in the size. Um, and that's a few numbers. I'll get back to that later. Let's look at an agenda we have for today. So just a brief explanation or understanding of what data science is. Um, Nothing really academic, just fun explanation. A key takeaways from data science group at SoftServe, as I said, numbers and maybe key facts that you probably don't know. And I hope you're going to remember what SoftServe is doing at that field. Trends I see in data science at the moment, like expectation from the client on the call I see and hear every day. That might be useful for you as well um, to shape your future career in that way. And then a few case studies that I'm not limited to talk about. So one public we did for the client and a few others that are mainly research or our internals. But before we start, here's a funny graph. I like to start with that. Say that's a price for a stock of the company that somehow related to the AI, and it's not Google. Google is actually a more stable, has a more stable graphic. Any ideas what the company is there? Because it helps drive the AI science really, really heavily. Um, Tesla didn't exist in 2002. Tencent, maybe, but still, they didn't start that early. No, SoftServe is a private company, so we don't have our prices on the market. So that price is actually for the NVIDIA company. So they were flat for the decade, I would say. And then the race that started about 5 years ago, it's not only cryptocurrency and mining, also it also takes like impact their business. It's also an AI, and the amount of the computational power they gave us to analyze that amount of data. So they actually equip a lot of data centers with their own GPUs, and that's actually almost the main driver of their business at the moment. So 5 years ago, if you were to buy a stock, you have to buy NVIDIA, and these days you would end up as a rich person. Good, so let's see what data science actually is. And as I said, it's not academic, it's actually that thing what I faced when I started my career as a scientist. So even today, the business not always understand what the science is. So both things, it's only always about money. It's rare people who can think about or doing this science work. Means they're expensive and they can give you a lot of revenue. Great. Customer usually think that science is the magic word and it can give you an answer to any question, or even without question you can have an answer. Like, here's my data, please give me an insight what you can do with that. Then we have developers or software engineers that treat our frameworks I would say our frameworks as the just something is ready to use, just print import science and then you can hit predict and that's it. Also it works to some extent and gives people a wrong confidence in what they're doing without deeper understanding what's underneath, what's under the hood. It's actually quite difficult to use properly all the tools that the data scientists right now work with. So like from my experience, science, it's everything. It's statistics, it's data sources, it's software infrastructure, and the importance of all that would be stressed in the second session by Hristo, who can explain deeper on the infrastructure and other things. So key facts about the SoftServe. As I said, we about 70 people size. It's only a data science group. The SoftServe overall is about 10,000 people. But still, despite we are quite small on that scale, it's one of the biggest data science group at Eastern Europe, if not the biggest. And this, we started about 8 years ago and growing since then. We have partnership with the all cloud vendors and the partnership with the universities like Technion, ETH Zurich, and the University of Texas. And we actually have people from I wouldn't say all around the world, but at least from 5 countries that I remember is the Poland, Bulgaria, Ukraine, United States, Canada. And we are focusing on the continuous development of our people. We are doing research and publication. In 2019, we had about 20 scientific researchers. In 2020, it was a difficult year and I didn't have a final calculation, but I hope it's still on the same level, about 20 scientific publication. And that's not something like a white papers. It's something you can find on archive publications. And what's I'm proud of almost the most is that we are developing ML not only for our clients but also for ourselves. So we are not afraid of doing science for the company and using it inside company as a production services. And about one of the production services I'm going to talk about today. So the trends I see at the market at the moment and things that might be useful for you. So at the left side, it's the Venn diagram. It's pretty old one, and I believe you're familiar with that. But what I'm see talking to different people and validating their expectation is it's not only takes for you to be like mathematician or computer scientist. It's also about thinking business. So you won't be a business analyst, but you have to be able to talk about business problems. There is almost no one literally who can translate a business need to the exact science problem. It's in most cases it's going to be you. Um, you are not an application architect, but um, people usually expect you to be able to at least to design a solution for the ML, means at least a component diagram, and then maybe a few options for the deployment, which services to use, and yeah, it takes time to get used to that thing. And as well as you're not a big data engineer, no one expects you to write a pipeline, but still you need to have a knowledge about how to run your data, especially these days when even I would say even a smallest data set wouldn't fit into the laptop memory, and you need to think about cloud or even using big data tools like Spark, for example, to run your data. So if you're about to choose where to develop next, in which direction, you can consider these three, either to choose a right domain, um, maybe improve your engineering skills or check what's on the cloud, and then think about big data and tools you need to analyze that big data. So that's it as an intro. I mean, the part that's not related to the cases I'm gonna to share. Hope that was useful. So let's then talk about the things we did. So the first case and cases I'm going to talk today, there are three. So they are all somehow related to the computer vision, and that's because of my personal background. As I said, I used to work with computer vision. So here it's a public case study. We work with a company called ABS, and their main business is actually to inspect a vehicle, a ship from the inside, and then decide whether that ship is allowed to go to the open sea, or it takes it should be dry docked immediately and then repaired or fixed or something. So for do that, they taken picture from the inside of the skull of the ship, and then there is a separate subject matter expert who sit in front of his laptop and evaluating every image. And that's obvious. It could be automated. And that was my first thought. It's going to be really simple. Basically, they are doing classification. So you need to decide whether the condition is good, poor, or worse. And like almost even the simplest model would solve this issue. But as you probably know, there was in details. See, the first thing they were asking for was the reasoning of the decision. And that means it's hard to provide that reasoning if you're building just a classification. Another thing was except reasoning to be able to fine tune maybe not the model but the decision boundary. So instead of having just a classification, they want to be able to modify the let's say threshold by which they decide what is the bad, what is the good, and what is the world class. And given all the information from them, we agreed to use a segmentation to actually to analyze those images. Segmentation for the corrosion and for the special structure elements like stiffeners and flat plates and well lines inside the ship. And again, despite the fact that it seems like it's obvious, it's just a segmentation task. Just take what's already there on the GitHub and adapt your model to the data you have. It's quite challenging. And why? It's because of this thing. I probably I didn't think about this as a quiz, but still, I'll probably ask you about the ideas. So here's the two input images you see, and the on the upper side you see a two interpretation for that images. Uh, what is the interpretation? Why was it so different? Any ideas? Maybe we don't have that much computer vision expert on the audience. Say this two interpretation per each images is actually not the result of the model, but the human interpretation. And that interpretation was done by different experts. So I hope you see, at least it's clearly obvious for me, how different these interpretations are. And when you think about like the first sort, as I said, it's so easy. Just take a data and feed the segmentation model for what you have. Then you realize that the real world data is actually that difficult, and the labels you have might be that bad. So uh, the message here is most probably when you start thinking the problem, the hardest would be not to find the right model and then to play with the loss function or just run the move duration or extend with the more automation, but actually the hardest problem would be your data and how you're going to fix that and how you're going to make sure your data is actually in a perfect shape. So at this project, and this, I would say that this is this actual valid for the a lot of different projects we are doing right now. It's not even a computer vision for everything where you need interpretation from the human. Once you have two person who's going to interpret your data, you're going to have a different interpretation, and you need to think ahead how to fix that and how you would work with that. In this case, we had a separate hard, I would say, workshop to convince people on to align on the set of rules how to interpret the images, what is real corrosion, what is real stiffeners or a flat plate, and how it's a what is the proper way to label all the things on the image. And only after that it takes us at least 2 weeks to run this workshop and to align this set of rules. Then it took for us maybe 2 months at least to collect a minimal data set of quality that is satisfying quality to actually to start any modeling work. So and that fun was like not that long. So when you already have all the data in place, you just take your cloud, a GPU, and a scaling to run as much experiments as you want and decide on the approach. But the painful thing is actually data, and that's my takeaway and hopefully a lesson for you in your future engagements. Um, so that's it about the ABS case. Hope that was relevant. Um, Another thing that I want to talk today is a digital signal processing. Also, again, it looks like a computer vision. It's not. It's a real digital signal processing. So that's our internal research. And after explain you what's happening there um, and how that can be used, it might increase your level of paranoid, to be honest. So the idea here is once you have a web camera or any camera and you see and you can identify a face of the human, um, you can actually analyze how the coloring of the skin here at the head on the forehead is actually changing, and then using digital signal processing extract the most important frequency. I would say it's much harder, but at least at a high level, identify the most important frequency, and that frequency is going to be responsible for your heart rate. And because that's not a computer vision, it's a pure digital signal processing. It's super fast. It works like a millisecond, I would say, on a millisecond scale. And why I'm warning you about your paranoidal thoughts, it's because having your heart rate monitored continuously, it's easier to validate how you react to different things. So if you stand in front of monitor and looking for something, uh, the machine behind that monitor can understand what you're looking for and what triggers you the most faster than you actually can realize it on your own. Um, I do have a video on how that works. Let me try to share that. Uh, it's gonna take just a minute, but it's better to see how it works. So it's a public video. It's on YouTube. So here is. Because none of the deep learning is used here. It's purely a digital signal processing. The girl should sit still because no one's actually tracking her face, but at the moment it's not an issue to track it. So before that she was calm. Now after the small physical exercise, we see how her heart rate is actually increasing and how that perfectly aligned with the Apple Watch on her hand that is tracking it really precise. So deviation from the result of the Apple Watch was less than 5%. And that's actually great achievement, I would say, for the signal processing and for the for the science itself. But as I said, it could be used, and it's already used actually in lots of devices and lots of services. Even here at Zoom, when I'm presenting, all my facial expression goes to the cloud, and it's easily to validate like what I'm feeling, how I react to different questions, for example, and so on and so forth. So that was an example of the research, and the next one is an example of the project we did on our own. It's in a production in Ukraine at Lviv city at our HQ. So we have a parking, obviously, in front of our HQ office. That parking is about 130 parking lots. And every time, especially if you come into work, well, before pandemic, hope that's going to change soon. When you come to work after 10 a.m., I would say, it take you, I don't know, a few circles around the parking to find a free slot. Even despite the fact that the parking itself is quite small, I mean, it's not that much space where you can do a few circles. It really takes at least 5 minutes every morning to find a free place. And the push was even from the upper level of the management of the company, because it usually they have a day starting at 10 a.m. and then they didn't include this 5 times gap into their schedule to find a parking lot. So they wanted to see where is the free parking lot there, right at the entrance of the parking. So what we did, we installed 2 cameras on top of the building, on top of our building, that's actually looking on the parking and analyzing it in real time. So here is the schema, how it looks in the production. And the funny fact again, if you think about automating parking, it doesn't sound that complex. You have just a camera, you have a video stream, you probably do have a plan of that parking, and you know, because it's a marked parking, you know where to expect the parking car, and you can just check each parking lot whether it's occupied or not, and eventually simplify this to just binary classification, because the parking is fixed, the camera is fixed, everything is fixed. You can just basically you can crop the image of every parking lot and do binary classification. Despite that fact that is that simple, it takes a lot of components to make it work in the production. It should somehow be integrated with the external system, and then it should be able to communicate to the interface. In our case, it's a monitor at the entrance of the parking. It should be able to report to security team. That was funny request, but still they are looking for the level of the occupation on the parking. And then deployment and storing historical images, because you want to keep that information and maybe use the data for the further fine tuning. So all that drives the complexity, and instead of binary classification that could be depicted as the, I don't know, 2 or 3 boxes, here we have that much components on a diagram. And here is actually how that looks, how our parking actually looks like. That's the, I would say, one of the best example, because there is no raining, there is no snow there. It's sunny day, and it gives a bit of shadows that impact the performance, but that's not the worst. So here it's at night. We are lucky we do have a few lightings on the parking, and even in a grayscale, it looks like it's pretty obvious and pretty easy for the ML to identify whether there is a car or not. And a bit worse at how it looks in winter. And that's not even the worst, it's just the beginning of the winter, I believe. It's in November, so it's not that much snow. And once snow is there, it's become really difficult, especially when everything is covered in snow. It's become really difficult to identify where is the car and where is just a pile of snow. And I do have a video that explains a bit how we come up with that and how it actually works. So here at the photo, by the way, at the left side, at the entrance of the parking, right to the barrier, you should notice the black square. It's a monitor with the live information from the parking. See, when you drive to the entrance, you already see what's happening there in a live. Okay, so let me share then the screen once again to show you a video how it's supposed to work.
While driving to any destination can be a hassle, parking shouldn't be. People get stressed when they waste time finding a place to park instead of getting where they need to be fast. What if it could be easier? At SoftServe, we're always looking for ways to automate processes and increase efficiency with our solutions. Here's what we came up with. Each space in the parking lot is tracked via video, which is analyzed by machine learning algorithms to detect open spots. Once the driver chooses an open parking spot, he proceeds forward. Another camera logs the car's license plate, verifying the authorized driver of the vehicle and eliminating the need for security cards or other ID verification. Finally, the driver is escorted to the open parking space without having to circle the parking lot even once. SoftServe delivers solutions-based services that make amazing experiences possible. We deliver the innovation, quality, and speed that our clients' users expect. Our technology expertise pairs with domain knowledge across healthcare, retail, financial services, media, and software. How will you take your business to the next level?
Yeah, so that was it. The drone you saw that was escorting the car to its parking place, it's like from the future that never happened, I believe. But everything else is already in place. So we do have that monitor at the entrance. We do have the camera that is tracking license plate of the car and opens a barrier for the authorized cars. And the camera at the entrance of the building with the Face ID, it's also there. And it having a hard time right now with all the faces covered with masks. So I know at the moment they are building a new data set to be able to work in new reality. So that's it, I believe, at the moment. That's everything I wanted to share with you. Maybe the last thing to mention about the parking. Again, the modeling itself wasn't the hardest or the biggest part of the the project itself. It's an ongoing project. We're collecting data, and we consider it as a playground for newcomers to play with new ideas. But the hardest thing was actually to deal with the data, to collect the proper data, to properly interpret the data, and then think about secure deployment and proper integration. And for example, license plates information that are stored somewhere in our internal database, how to get that to then validate these license plates at the entrance of the parking. So that said, the romantic of the science, unfortunately, is about 30% of usual project, and most of the time you are dealing with the data issues or building a pipeline on thinking about integration or thinking about architecture, how it's going to be looking as a production, and thinking about this in advance. So that's it from my side. We agreed to have questions at the very end after the second after the second session. So yeah, that's it. If you have any questions, please note them down and be ready to ask after the Hristo has his talk. Hristo?
Okay, so thank
Sergey,
you. Thanks.
right?
Yeah. Thank you, Roman. Yeah. Yeah, it was interesting case. I mean, these three cases are they're really interesting about the vessel inspections, pool detection, and smart parking. Yeah, I have. Yeah, you mentioned about data, so that was going to be one of my questions. But yeah, let's see. Well, let's see the Q&A session. Now I want to introduce Hristo, who is from Sofia office, from the office in Sofia. What about him? He liked rock climbing, and what else? And he's having a dog at home. That's what he shared. But also what we know that he's going to present us a very interesting topic about MLOps, about something which I really love to hear, because I mean me personally, being in a company which I manage, every time we struggle. Once we have a model, then from the experimentation mode, how to put it in production, and this every time is challenging. And when I speak with different people, different friends of mine, they're using different approaches. So I'll be so happy to see the Hristo presentations. For those of you who doesn't know what MLOps means, it's like it helps to facilitate or streamline the organization of ML process, machine learning processes. So he will tell us more about it. And Hristo, let's roll.
Thank you, Sergey, for this introduction. Let me share my screen so we can get started. Okay, so basically, let's talk MLOps. What is MLOps? Basically, MLOps is a set of practices that will help you manage your machine learning projects lifecycle and ensure that the machine learning you push to production is the thing you need really, and not something that will cause you problems. My background is quite diverse. I've worked on many machine learning projects, and many of the challenges that I'm going to present and how to solve them, I've already had the pleasure to solve personally on several occasions. So let's get started with the brief introduction. So where are we with AI? So we've all seen this graphic. You can see that AI can be pretty much quantified as numbers of neurons. Right now we are here. We are at the small rodent level in terms of numbers of neurons. Machine learning is pretty good at computer vision, playing games, text-to-speech, and driving cars. So what are the challenges to bringing AI to production in general? First of all, as Roman already mentioned, the biggest challenge is data. Like you don't necessarily need a lot of it, but you need really good quality of data in order to achieve proper results. As they say, your model is only as good as your data is. The second challenge is that in many cases, machine learning projects have kind of unclear success criteria. For a classical programming project, you'd have a desired quality, a business case, and after analyzing its behavior, you can confirm the quality of the project and that you have achieved your goals. With machine learning, it is not always the case. There's like competing scores you need to compare, and you to decide which score is important for you, and also to explain to business what all this is. The other challenge is scaling workloads. So with more data, you need more CPUs, more RAM, like with more complex models that also scales up significantly. So you run into some scaling problems with training your models and actually serving them, because they get heavier the more complex they get. How is AI faring in practice? Here is an interesting study by Gartner. They have surveyed several companies, and they have discovered that only 47% of models get fully deployed, and like 30% get partially deployed, and 24 don't get deployed at all for some reason or another. Why is that? How is ML perceived? Like when people think ML, they think that it's just model training and tuning and you're done. This is far from the truth. So model development actually includes multiple steps. First, you need to ingest your data, you need to analyze your data, you need to clean your data. This is very important nowadays. Then you need to discuss what features are most appropriate to train on, and then you get to train the model and evaluate it and get your scores, which you can judge your success in. Okay, are we done? Almost. Now we get to the hard part, getting stuff to production. Pretty much you need to re-implement all of your development logic into production-ready software. It is not necessarily a copy-paste process. Sometimes the production platforms will not allow for like pure Python from your notebook books to be directly transferred. So you need to re-implement some stuff. You need to think about like automated deployment of your pipelines, auto scaling for loads and so forth. And after you do that, then you can plug in your model. So this perception sometimes reflects into how teams are structured. You sometimes see a disproportionate amount of data scientists to engineers. And in the worst case, if you don't have the luxury of having ML engineers, you just have to like try to explain to like regular engineers how to deploy a model, and in that case, data science teams get involved into engineering, and you're kind of mixing roles. So this results in this sort of a timeline for a machine learning project. The actual machine learning and like discovering the model, tuning it and so forth can be done fairly quickly. And like this is what Roman confirmed. Like only a couple of weeks you can get a working model in a sandbox, and then you can get several months of coding to get it ready for production. And even after it's ready for production, you still can end up with many problems that you might have missed. For example, you may end up with no production model monitoring, or you may end up with stale models, or what I've seen many times is that there isn't a separate development or production environment. You just test stuff directly to production. There's little or none automated model training, so you may end up with a lower quality product than you wanted to. So here comes MLOps. Can we do better? Well, of course we can. So first thing you need to do is you need to think about machine learning as a cyclical and iterative process. It's not like you build a model, you train it, you ship it, you're done. It's not like that. It is just like any other software development process. You can have several intermediate products before you reach the one you need. With the difference from standard software processes, you need to think about model training as something that is sort of unpredictable. Like you're never sure what model you'll get. It all depends on the data and the parameters, and it is something that you need to tune iteratively. So what does an iterative process need? First, it needs a clearly defined process. Like if you start heads-on with just developing your machine learning without any concern of the process, you will get into unexpected issues. You will run into like delays with the project and so forth. The second thing that you really need is data set and experiment tracking. Like we're all used to working with our notebooks. Like you can spend your entire year in Jupyter and source control like every other day and not track your experiments at all, which kind of works, but we can definitely do better. And so a third cornerstone is consistent model quality control and code quality control. Code quality control, it's fairly well defined. You can find lots of toolkits and resources online on how to do it. And you also have a decade of DevOps already available for you to leverage on. But you also need to control the quality of the model. So special considerations needs to be taken before shipping a model to production. And last but not least, you really need tooling. Tooling can save you a lot of time, and since it is an iterative model, machine learning can benefit a lot from automation. So let's talk about these four things. The first thing that we need to address is the processes. Like, as already mentioned, machine learning is an iterative process. So you first start with an idea, then you frame it into your business context to see what kind of value you're expecting from it. And then you hand it down to the data science team to collect data, do feature engineering, train it, and evaluate the models. And obviously, this needs to be done several times before you achieve something that is production ready. And once you're happy with the models, you don't ship the models themselves. You ship the code that creates the models to the operations teams. And these models are then, this code is then transformed into pipelines, which can then be deployed to production training, which you get the actual model that you end up serving. So, okay, you got the models displayed, you have it working, it delivers value. What do you do next? You monitor it. After you monitor it, you analyze its performance over time, and you use the analysis to come up with ideas on how to improve it, like what you can add, what you can remove, how you can get more value for your business. So the whole cycle goes in the same circle again. Like I'm stressing this a lot because I've seen this in practice. This process really is iterative. If you think about it as a linear project, you will end up with cost overruns. One of the most important things about MLOps is the notion of reproducibility. The notion that you should be able to have clear view on what you were doing 2 months, 6 months, 10 months ago. And you need to know what data you were using, how the features were prepared, how the model was trained, and what the actual model performance was. So the first and most important thing is to track your data. Data can get really messy really quickly. Sometimes data sets can get really big, and it is really important to have them versioned. You can just have several copies of them, like version them through directory names, or you can use specialized tools which are already available, like both open source or in the cloud. So I strongly recommend that you version your data sets. Like you don't train something on one data, then change data and make it impossible to reproduce your results. This will cause you problems down the line. The second important thing is to store the feature transformation pipelines. The easiest thing to do it is to keep that code in Git, but there are cloud solutions and also open source solutions which allow you to specialize for these tasks and will allow you to keep really good track of both your data and your feature engineering, so that you have complete visibility of the history of your experiments. The next more important part is training. Obviously, this is considered as the most important part, but it is the easiest to track because it is just code, mostly Python. So you just source control it in Git. So what do you do with the ready models? It is a good idea to save those as well, along with all of their metadata. Like you need to know how this model was trained, like with what training code, which features, and which dataset version. There are already solutions that are called model repositories. I strongly recommend you use those. They will bring a lot of value to your process. And last but not least, you need to track what's going on production, like when you serve the models. And you do that by tracking the production logs. You need to track both what the model is given as inputs and its outputs. This will be invaluable in the future when you need to improve on your model quality. The third cornerstone, as already mentioned, is quality assurance. So we already know how to test software, like tools are available. It's been a long time since we started doing test-driven development. So feature engineering, training, and serving is fairly easy. It's mostly pure code. So you just perform standard unit testing. Data, on the other hand, is special. Data, both in terms of training data and production data that goes into your serving infrastructure, need to be tested regularly for missing values, schema violations, missing columns, and so forth. This is especially important if you're doing, if you have like a production model which uses data from other systems. These other systems very often are maintained by a team that is not yours. So they can push some version, they can change something, they may not necessarily not notify everyone involved. So you may end up with data that is not what your model expects. So You may end up with missing columns. You may end up with a column full of no's. You may end up with 2 new columns, which your model will not know what to do with. And the worst things about these problems is that they fail silently. So if you give your model like incorrect inputs, something that it does not expect, the model sees just a bunch of numbers, and it will give output regardless of these numbers make sense or not. It do not necessarily cause an error to be given, and this can go on for weeks without anybody noticing, especially if you don't have monitoring for production model performance. So that's why I recommend that you put explicit checks on your incoming data, especially if it's coming from a system from which is live and you don't have direct control over. The next thing you need to give special attention to is testing your models. This is kind of tricky. So you need to test your models not only by how well they predict, the mean squared loss or precision or recall in terms of classification. You need to make sure that your model works well with all sorts of data you can throw at it. One common approach is to slice your data into facets by some feature and see if the model performs in all types of data. The other thing that you need to be careful about is model fairness. This is kind of a new thing in the recent years. So you need to make sure that your models performs equally well if it's regarding men, women, and it should not discriminate against race or so forth. So that is something that can be tested automatically and should be tested regularly with every update of your model. So how does this all fit in terms of a solution? So you start with your data, and now it's called the feature store because we skipped here the ETL. So at first you do experimentation on it. You do data analysis and you build your experiment pipeline, which has all the components that we already discussed, like validation, preparation, training, and model evaluation. This is what the data science team is expected to do. So after the model is analyzed and it is confirmed that this solution gives appropriate results, you take the machine learning code and you put it into a repository. Sorry. To make it source controlled, usually Git, and you pass it on to the operations team, which orchestrates the deployment. So this green pipeline here is in, for example, Kubernetes or some other cloud solution. It does the same thing, but it is source controlled and deployed automatically. So it uses the original feature store, and every run of this pipeline needs to be recorded in the metadata store so that you know exactly what parameters the data was run on and which data, which code version, and everything that is important. After this model is then ready, you put it in the model registry and you proceed with the release and deployment of the model solution. In the end, pushing in the trained model into the prediction service. So the prediction service will then use data as already discussed, and viewers come up with its results. Of course, everything is logged and monitored, and this information can be fed and is recommended to be fed to help retrain the data in the future. So basically, This whole bit is automatic. No humans work here. This bit is the only place where you have humans. Humans only develop the source code and the orchestration, deployment. Everything else happens in the cloud. So if you have like model retraining, you can have this pipeline run automatically. You can use monitoring to trigger the pipeline if you see that the model is going stale. You can use this monitoring to come up with to trigger more development from the data science teams, so that they can then again push a newer version of the pipeline, and the process goes on again. So everything is cyclical, everything is automatic. A lot of time is being saved this way. So how does this look in the real world? This is an example architecture. In this case, everything is deployed in Azure ML. If you're not familiar with it, the Azure cloud has a really good and mature machine learning and MLOps platform, which gives you pretty much tools to do everything that I spoke about today. So what we're seeing here, first we see the business. They're producing data, which is then stored into the business data lakes, which is used for purposes other than machine learning, but we are using it for that for now. So within Azure ML, we have two pipelines. We have the training pipeline and the prediction pipeline. As you can see, the ingestion and ETL section of this pipeline is the same for both ends of the infrastructure. So in training, you ingest data, you put it in a training pipeline. Azure ML provides the compute for it. You can even use GPUs. And you can also validate it with your own metrics. And once you're sure that this model is like worthy of production, you push it to the model registry with the appropriate tag, so that it is then treated as a production model. What we do in the prediction pipeline, it basically has the same logic for ETL. It just uses new unseen data from the same data sources. It would pull the model from the registry, it would apply the model, and it will automatically push the result to the dashboard to be consumed from the business. Everything can be managed by Terraform, and everything is managed by Azure ML DevOps, Azure DevOps. And for example, data tracking is done with Azure ML. Here we have the icon here, but it does have the provision to track for model versioning. Metadata version tracking is also tracked within Azure ML. And model registry also tracks experiments and their performances. Within model registry, you can see exactly on what code the model was trained and on what data. So you have full reproducibility. Oh, one more thing, really important. Like since everything is deployed automatically with Terraform and Azure DevOps, you can spin up as many instances as you want. So it is really easy to have a development instance, a staging instance, and a production instance. So it's easy for developers to have their own dev sandboxes to play around with without putting production in danger. So having spoken about the tactics, let's talk about what they bring us. First of all, they bring us reproducibility and auditability. So every artifact is tracked and can be audited in the future. This is really important because in machine learning, if you change one thing, it changes everything. So one single line of data can completely change your model output. You have automated pipelines, which are source controlled and verifiable. You have code deployments with using DevOps practices. You have fairly good validation capabilities to enable minimizing model biases. You have the ability to check beforehand if the module will perform well online or offline. And of course, quality control for your code is essential. In terms of automation and observability, you have like the standard controlled rollout capabilities, which will help you deploy everything quickly and reliably without too much issues. So what is the current state of the MLOps? So a brief history. Before the year 2000, machine learning was pretty much the domain of proprietary services and products. So there wasn't much freedom outside these products. After that, open source came and the Python stack exploded. So you have some really significant tools which democratize machine learning by a lot. You have scikit-learn, you have TensorFlow, you have Apache Spark, and so forth, which allows you to do some big data. And this opened doors for some really exciting projects. But everything changed with the advent of the container, which allows you to have a more reliable sort of environment. You can be pretty sure on what your production code will do and the model before you deploy it. So it gives you like the really good reproducibility. And later on, we have the advent of specialized machine learning platforms, machine learning MLOps platforms, sorry. So where everything is deployed automatically, they leverage Kubernetes. You have already tools to track your dataset versions and your models and performance. Everything is much easier nowadays. In terms of tooling, MLOps has recently exploded with a lot. So for every aspect of these processes, you pretty much have a tool and actually have several tools to choose from. In terms of the big cloud providers, as I mentioned, they all have their own MLOps integration platforms. I'm personally really fond of Azure Machine Learning because it really provides an end-to-end tooling solution for the entire MLOps process. I'm not sure how familiar you are with the hype curve that Gartner produces every year. So you can basically what this is how much is expected of a product or practice over time. For example, we see that MLOps is now at the top of the hype curve. There is a lot of talk about it, but it is yet to be a proven technology that is widely accepted by like the majority of enterprises. As you can see, for example, notebooks and Apache Spark are now widely accepted. There's nothing exotic about them anymore. They're like everywhere. Deep neural nets are now on the decline and towards the maturity end of the curve. And with MLOps, we're yet to see it widely adopted. We're kind of expecting it to become the staple of machine learning, not just because this is what I specialize in, but it really does improve the quality both of your projects and of your project's lifecycle, and reduces the amount of stress on every level of the ML pipeline. So thank you for your time. It was a pleasure for me to present this information to you. I hope I was useful. Guess it is time for Q&A in a couple of minutes. And excuse me for this shameless plug, but we're hiring. So if you're interested in MLOps, feel free to find our openings on our website.
Thank you, Hristo. Yeah. I mean, I really like the presentation. What I see also for the questions is that people like the style of your presentation also, as long as the content itself. There was a question about the recording and presentation. I saw two questions. One of them is answered. So tomorrow, I mean, after the meetup, SoftServes are going to send the link to all participants to their emails. What else? Amazing explanation from Tofi. There is a question. I don't know. Probably for some of you, Hristo. What about people with no experience?
Well, basically, these practices can be learned. It's nothing. It's not rocket science. It's just software engineering with some machine learning. Basically, what a good MLOps engineer would be is either a DevOps engineer who knows some stuff about machine learning, or like a data scientist or machine learning engineer who has some knowledge in DevOps, which is pretty much my background. Like I started off as a data scientist, and having to deal with all of the problems of deployment myself, I ended up solving many of the problems I just discussed by myself without too much of structure. So if you're interested in this field, like the things you need to have at least is like some DevOps experience, like automation and deployment. Like you need to know your containers and your Kubernetes and your stuff. And in terms of machine learning, it does help to know a lot of it. But basically, if you're familiar with the lifecycle and the tools that you need, for example, TensorFlow and scikit-learn, you're pretty much ready to go for such position.
Okay. Yeah. Thank you. Also for the rest of you, you can use. I mean, you started using question and answer. So if you have also questions for Roman, please write them now. Write them now because we are going to answer now. Something else, we have another. I mean, Marianne says great presentation from Bobby. All of these frameworks seems like they're for large models, companies. Are there alternative for small projects, companies? I cannot hear probably are and which are cost effective, because some of them seems probably, if you can give us a range of how much it costs for a month also.
Well, basically, if you want to implement Azure ML, the Azure ML platforms in the cloud are pretty much free. You only pay for the resources that you use. You don't really need to pay for the tooling, for the data, for the model registry, or for the deployment pipelines. Everything is free, and you actually end up saving money using cloud because you end up with less money for maintenance and salaries. And also, one really cool thing about MLOps is, like, if you do it properly, you can actually save a lot of money just by using the cloud how it should be. For example, Azure ML and say like Amazon SageMaker have this toolkit where you can pretty much leverage AutoML to a really good extent. So instead of hiring like a GPU instance and training one model, waiting for it, training the other model, waiting for it to finish evaluating, you can basically spin up like 20 GPU instances train the models in parallel, and evaluate them on the same day. And in the end, you pay exactly the same as you would have paid if you used one GPU instance for 20 times the time.
Okay. Okay, so there are again several questions for hiring. I think that for hiring, they can make just to make them offline, so they can continue the communication via the emails. Something else from Petya Vasilieva, she's asking, are you using, have you ever had cases in which ML was not appropriate? What she means, I mean that simpler data analysis techniques were more appropriate than ML.
Oh, of course, plenty. Like this is pretty usual. You start with the ML, you find out that it's not working, and you search the like domain knowledge, and you end up with fairly good results just using a couple of rules. So this happens all the time. Like ML is not a silver bullet.
I guess, guys, you didn't forget Roman presentation, because I didn't see any questions for him. So, Roman, I will ask you about I was interested with the vessel inspection, about the data and data quality, how the data was captured. I mean, and what are you using, the RGB pictures, or there were infrared pictures? I mean, something, because you mentioned that it was hard there, but if you can give some insight.
Yeah, that was purely RGB images, and the hard part was that they were taken with the cheapest available either phone or cheapest available digital camera, and that picture are taken inside ship's skull, and it's not that much light there. It's all like it's your headlamp maybe and a flash on a digital camera. So yeah, that's it. No special equipment, and to be honest, it won't help you to have a thermal camera or infrared camera or anything else to detect rust.
Okay. One question again about pulse detection, because we all know that ML, we want to be explainable. At the end, when you, I mean, there are different techniques like heat maps and this kind of stuff of the features. When you make for the face, I'm curious where exactly from the face the pulse was most reliably captured and predicted.
Yeah, so it's not from the face, it's from forehead. Here, everyone has a vision, goes a bit like a diagonal. I don't know whether you see my showing on my head. So it's an anatomic, it's invisible, just naked eye. You can feel it by, like, if you touch, you can feel it. But despite the fact you can see it with a naked eye, it's still when blood is pushed through this vein, the coloring is changing a bit, and that's enough for the algorithm to notice that frequency.
Okay, so you need to have a good camera again.
To be honest, that was just a webcam. Well, maybe not the cheapest. It was just a standard web camera on the it wasn't even a laptop. It was just a desktop. What we start with, nothing special. Just I don't know how much, $15-20 camera, and it's already capable of doing that.
Okay. Yeah, we have one question from Peter Stefanov, or Peter Stefanov, let's call it in Bulgarian. And he's asking, how does MLOps enable one to track each of the data scientist experiments, even the ones that did not yield good results? I mean the experiments that are not scheduled for automatic.
Yeah, you can totally do that. Like every tool that I've seen so far has, it's basically just an API which you can plug into your notebook and just add it as just another line of code. So it's up for your organization itself to decide whether they want to track the unsuccessful experiments. In my opinion, this is highly recommended, but you need to put the appropriate metadata, like to say, yeah, this person ran this experiment with this exact code, otherwise it's useless. So you can use a model registry in pretty much every context you can think of. It's just an API you need to authenticate to.
Okay, yeah, thank you. We have one question for Roman again. What was the sampling frequency used for measuring the heart rate?
Yeah, that's a funny one. So it's about 20 FPS, but that's enough to track the frequency of the human heart.
Okay. I think that's it. I have one question which just popped up for Hristo, because when you're making the model, normally because in the diagram which you show, normally it needs to go to test environment and then it needs to go to production environment. So was that all integrated, or for the sake of simplicity, it was not covered in the diagram?
You're talking about the cloud diagram with the actual solution.
Yeah.
Okay, let me bring it up.
Yeah, because normally in my company, every time we need to test it before deploying it.
So like the testing of the code is done in the sandbox. Also, we test the entire pipeline with the metadata. But so there is no testing of the actual model here. We just have like a set of quality measures that the model needs to cover. For example, it needs to work with several strata of data, and it needs to produce consistent quality with old data and new data, because mostly this particular solution works in time series. And like you can go as deep as you want, but for models, I think you can. This is technically production, the training pipeline. So, but still, you have some sort of testing and validation that is automated in there.
Okay, yeah, I get your point. I was considering, because normally we are doing two separate environment. One is testing, one is production, because sometimes the real production,
Yes, I got that. Now I got your question. Yes, in this particular solution, there is a staging environment and there is a production environment. So this entire infrastructure is also available in staging, when you can test the entirety of it with real data if you want to, and you can actually compare it with the currently running production deployment. So it's sort of like a canary deployment.
Okay, thank you. And one final question is for Roman. How long did you train the model for the rust detection?
So the whole, like how long it took us to come up with the final model was about 2 months, I believe. I mean, that was not a training purely, it was more of searching what's gonna work the best. In terms of training model, it was different, but it wasn't that hard, because the data set was collected manually and really narrow just for the corrosion detection. So the training took maybe half a day for every experiment.
Okay, so yeah, I think this was the last question. So I want to thank you. So applause from me, but I assume that all the audience will applaud Roman and Hristo for these really good presentations. Something is just to remind to the audience that next month we will have our next meetup, so stay tuned. Also to thank to SoftServe for this great speakers, and we hope work together with them and promote such a good practices. Also, if some of you want to be a volunteer and be part of Data Science Society, so just shout out, find us on Facebook or LinkedIn, write us there or via the email. And thank you, Roman, thank you, Hristo, thank you, bye.
I guess, thank you.
So